So the point of recursion here and learning recursion is so that we learn, we get ready to deal with recursive data structures. Now, we're not going to learn anything new this week, but when we start on trees, we are definitely learning some new things. We are going to be definitely learning about recursive data structures, because the tree is a recursive data structure. Now, so let's go ahead and take a look at it. So recursive data structures, we often want to look at a data structure like a linked list and maybe say, hey, it may be better for problem solving purposes that we look at it recursively. Linked list is a classical recursive data structure, but trees are even more kind of that way. It is, as we saw, we can code a linked list without recursion. Doing so with a tree, a bit more difficult. And recursive methods, we'll see that these are actually, we can write really short and powerful methods using recursion by looking at the data structure in a recursive manner. And what does that mean? Well, the idea here is that, let's suppose we've got this linked list here, right? We've got this linked list here, 5 nodes in it. Well, each node in this linked list, the way we're going to go when we process something is that we're going to view each node as though it was the head of its own linked list. So if we're looking at this node, we view it as not only is it the actual head of the entire linked list, but we view him as as a node that starts here, and then after him is another node with its own linked list of its. So we kind of view it that way conceptually. We don't actually program it that way, but we view it that way conceptually when we, there's a new linked list class. He still points his head.next is still another node. It's not another linked list, but we're going to program it as though this guy is the head of his own linked list. So this guy, we can view him as like the head of a linked list that has 4 nodes in it. We can view this guy as a node that has, as a linked list that has 3 nodes in it. This guy's the head of a linked list with 2 nodes. This is a linked list with nothing after him, right? Each guy views himself as basically the only important node in the list. And everybody after him, he doesn't know what's after him. All he knows he doesn't know, like, if there's 10 nodes, 5 nodes. He'll know if there's either null after him or the head of another linked list, another slightly smaller linked list. Right? So a linked list is a collection of nodes such that each node references, another linked list consisting of the nodes that followed in the list. Last node, after it's followed, it is an empty list. So we will program basically a lot of these methods recursively. So I'm just going to go through the slides rather than coding out myself and show you that we can look at a lot of the classical methods, like adding to the end, calculating the size of the list, removing a node from the list recursively. So public class. So we're just creating a new linked list class, linked list rec. And we notice we aren't going to keep track of the size. We're just going to, the only thing we're going to keep track of is the head of the list. So here we have a recursive size method. Now notice we have 2 of them. We have this wrapper method, which is just simply what the user is going to call, or the developer is going to call, so that they don't have to deal with the internal way that this works. They don't have to provide any of the arguments for it to work recursively. And all this does is says return size head, and this returns the size of the linked list that starts at head. All right. If head is null, that's our base case. We return 0. Else, we're going to return 1 because we know that this linked list has at least 1 node in it, which is head, plus the size of the list that comes after head. Right. Head.next. The size of the list that starts after it. So in our example here, right, if we called size, we'd ask for the size of the linked list starting here, and it'd say, oh, it's 1 plus the size of this linked list. And this guy would say, well, that's 1 plus the size of this linked list, 1 plus the size of this linked list, and he'd say 1 plus the size of the linked list that starts over here, and he'd say 1 plus the size of this linked list, which happens to be 0, so I'll return 1. And so he goes, okay, got my answer, I'll return 2. Oh, I got my answer, I'll return 3. Oh, I got my answer, I'll return 4. And he goes, okay, I got my answer, I'll return 5. This does take O of n time because we have to basically physically count. Maybe we make one method call for every single node in the list, right? So not the most efficient way, but for demonstration purposes, it's great. Similarly with toString, right, what we'll do is that we will say, let's print out the string representation of the list starting at head. So here, head. And again, the head argument here refers to not like the head this isn't the head instance variable, this is the head local variable. So this is the head of this recursively defined linked list. Right? So if the head of this local variable head is empty, then we return empty. Otherwise, we'll get the data from it, print out a new line, and we will go ahead and convert head.next into a string. Right, we'll convert the list that starts at head.next into a string. What about like something more interesting like adding? Okay, so here, let's go ahead and look at our base case. And here we have both of the public and private have both the wrapper method and this method have a base case and a recursive case. So we're going to add data here. If head is equal to null, if the head is empty, right, if we have got an empty list, well then the item we're adding, we're just going to slap it onto the end of the list, right? This works just the same way. We're going to add this data to the end of the list. Create a new node, and it gets set to head. Otherwise, if there's data there, we are saying we want to add this data to the end of the list that starts at head. So here we're in this method. We want to say we want to add data to the end of the list that starts here at head. If there's nothing after the head, this is our base case, then we are going to simply create a new node and attach it to the end of after this item, right? If we've got an empty list after the head of this current linked list, then well, we'll now have a node after it. Otherwise, well, I don't know really how to do that, right? So I'm going to tell the list that comes after me, hey, attach this data to the end of you. So right here, say I wanted to add an item to the end of this list. Head would go, well, that's a bit of a job, so I've got no room because I've already got somebody after me, but why don't you go and ask him how and tell him to add something to the end of his list. And he goes, well, why don't you tell the node after me to add an item to the end of her list? And she goes, well, why don't you tell the node after me to add a node to the end of the item, to the end of the list starting at this guy. And this guy goes, oh, well, add a node and the item to the end of the list that starts with him. And he goes, I've got an empty spot, so go ahead and just add this node right over here. All right, suppose we want to do a recursive remove from this list. Okay, so here we've just skipped the wrapper class entirely. Oh, nope, it's on the other page. So let's go ahead. Say we want to remove this data. So if it's an empty list, obviously we couldn't remove the data. Otherwise, if the actual head of the list has the data, we just do the classic head is equal to head.next and say, yay, we removed it. Otherwise, we tell the guy after me to remove. So we want to say remove from the list starting at head.next, remove this data. And in case you do have to remove the guy after me, here I am so that the list doesn't completely get all tangled up. So we'll see how that works in just a second. So here we're saying this method says, okay, I want you to remove out data from the list that starts at this node head. And here's the predecessor, the guy before head. If head is null, well, that's a base case. We can't remove out data from that list, so return false. Otherwise, if the other base case, right, if the data in head is equal to the data we're trying to remove, we say pred.next, we say the guy after head, sorry, the guy before head, his next item should be the guy after head. And so that's how we'll remove head. So we'll remove head from the list by doing this, pred.next is equal to head.next, and return true, because we're done. Otherwise, well, I'm not, the head goes, well, I'm not null, and I don't have the item you're looking for, but maybe the list after me, the list that comes after me, they might have the data you want to remove, so why don't you remove that? right? So let's go ahead and say we're removing 5 from this list, right? Not index 5, but the number 5. So head goes, oh, we're going to go ahead and keep track of, let's go ahead and, right, so let's see if I can't be clever about this. So I'll use P for pred, right? And head, what will happen is that we want to say we remove 5. Head will go, oh, I can't do that. Ask the list that starts at this guy to remove 5. And he'll go, okay, well, I can't do that, so ask the guy after him to remove 5. And P will have gone from here to here. Ask this node to remove 5, that starts here to remove 5. And you'll want to keep me along, and you'll want to keep knowledge of me just in case you do have to remove this guy over here. And he goes, okay, I don't have 5, so I'm going to tell the node that's starting at the next guy to remove to remove 5. And you'll keep track of, and I'll keep track of me just in case, and I'll pass myself as part of the method just so you can keep track of me in case you need me. And finally 5, we get here and he goes, I have 5. Well, drat, I guess I'm getting deleted. So we'll use the information that got passed in with me to point this arrow to skip over me. That way I'll get garbage collected. Alright, so we can, and you can code this up and you'll see, or you can find the code yourself. It's recursive linked list rec.java. You should be able to probably find it online. You see that this basically is just this is a valid way to look at a linked list, a valid way to look at, this data structure. Right. So we'll go into way more detail about this with when we get into trees, but this is kind of where we're heading with this. When we deal with trees, we're dealing with a purely recursive data structure.